Okay, well, I can start by saying welcome, everybody. It's really exciting to have you all here. I'm hoping that this class is going to touch on some pretty interesting aspects of how category theory is used in modern mathematics, but whilst also giving the foundational ideas. So it's going to be introductory, but we're going to be trying to introduce it as close to the way that it is truly used in the modern day as possible. And as has already been mentioned, the secondary goal for this course is to kind of give some words of wisdom or some general guidelines, or to start getting you all in the audience to think about how you would present a theoretical concept, be that an aspect of mathematics, or be that an aspect of theoretical computer science, or be that an aspect of musical theory, or like the theory of art, whatever it is that you could possibly be motivated to present. But the only loose constraints that we'll be restricting ourselves to would be theoretical ideas. So in an academic setting, how do I present a theoretical idea? Okay, so the course is called Shadows of Computation. I think it took Billy and I about 2 months to come up with that name in the end, but it is what it is. And the reason why we named it this is because we want to ask the question, what is computation? And how does it get actualized? So one motivation for category theory is, I suppose, the motivation coming from the computer scientist's perspective. So let's draw a subheading here, computer science. And try to understand why the above two questions are distinct and how it gets realized and how maybe category theory could be useful for that. So in my opinion, one of the many influences, one of the many great influences that computer science has had on mathematics over the last century would be the divide, or the realization that there is importance in making the distinction between syntax on the one hand and semantics on the other. Speaking very loosely, you can think of syntax as the language, and you think about semantics as the meaning. Now, I don't know if I've triggered many people in the audience by using the word meaning already, but allow me to speak vaguely for now, and we'll get more precise as the course goes on. But what could one possible way of understanding this split, or studying this split formally and rigorously, without getting completely caught in impossible to be objective about philosophical problems, right? And this is where I would say, well, this is what motivated my statement that this is one of the great influences of computer science on mathematics, because indeed this is possible. So what we do is you construct a particular language, and then you think about the structure of that language, and you construct a mathematical object out of that language, and that object is going to end up being an example of a category. So over on the syntax side, we have these things called syntactic categories. And these are kind of ridiculously formal things the objects inside these categories are often equivalence classes of literal statements that you can make inside the language that you've decided to work with. So, so I mean, like, we're being as just insanely technical and precise and literal about language as you possibly can be on the syntactic side. So what's a language? Well, it consists of an alphabet, and then over that alphabet are the allowed words, and then using those words are the allowed sentences. And then once you have the sentences, there are arguments or proofs, which are particular combinations of those sentences, etc. And then we want to make the observation that sometimes there are many different sentences that say the same thing. So we want to draw some kind of equivalence relation between these things. That is what this type of object is here. And we can do that very, very precisely using category theory. So that's the language side, but then you kind of have a really interesting question. You make the observation that on the right-hand side, well, there exists a whole lot of, let me say, mathematical categories. So this might be the category of sets and relations. That's one example of a category. You might have something more exotic. You might have quantum error correction codes. Or perhaps other things. We will see later that the definition of a category is incredibly liberal. So lots and lots of things become categories. Maybe just as a random example, you might have topological spaces. And then the game that we want to play is, can we draw formal relationships between the syntactic categories and the semantic categories? So if I can in some way map this syntactic category onto these quote unquote mathematical categories, then I can start exploring relationships and feedbacks between these two categories. So syntax has structure. For example, you can rewrite proofs. If I have a proof of a particular formula, I can rewrite that proof that eliminates a particular uh, uh, logical law, which I might not be. Let me make a better statement. So you can prove something efficiently and you can prove something inefficiently would be an example of how you might want to transform a proof. So you write something down because it works, and then you want to manipulate it to reach some kind of canonical form that you think is reflective of inherent structure inside that language. You can then ask yourself, how does that rewriting get mapped through these blue lines that I've drawn here? I'm sorry, I'm getting insecure about my voice. I'm sick at the moment, and you can hear it starting to go. I'll just have to try and speak a bit quieter, I think. Okay, so that would be one direction, going from the rewriting systems inside syntactic categories and seeing how they follow through into the semantic categories. Maybe we can find mathematical structure inside these categories that we haven't thought of before. And maybe there's a feedback in the opposite direction. Maybe if we look at these semantic categories, we notice that there is even more that exists inside these categories than just that which is reflected by the syntactic category. In such a situation, we can think about extending the syntax, and this is a method for constructing logics. And the philosophical point is that you've done more than just construct it randomly. Maybe we've actually discovered true structure of the syntax that was there all along, but we didn't realize it because we didn't have that perspective coming from semantics. Okay.
For what it's worth, Will, you sound exactly the same to me as you always do.
What, really? Oh, okay. I think of my voice. But thank you. I'm glad that it's not noticeable. Okay, so that would be a very computer sciencey relationship, sorry, motivation of category theory, because as as a theoretician, you want to be asking yourself, that's a very good dream to draw this relationship between syntax and semantics, but we don't even have the mathematical structures to do that. If I were to use group theory, I need everything to be a group. Maybe that's too restrictive. If I were to use set theory, everything has to be sets and functions. Maybe that's a little bit weak. And so there's demand for greater generality upon which we allocate categories, like literally categories. There's category of thought here, being in topological spaces. There's category of thought here, being in syntactic categories, etc. Whilst I'm in the neighborhood, I'll very briefly give a logical motivation for category theory. Because it's very similar to the computer science motivation. And there are a number of different reasons why, but there is one theorem in particular that has been incredibly influential in the relationship between logic and computer science, and it's the so-called Curry-Howard correspondence. And this is the I believe, first example of the program that I sketched earlier, where you make your observation that your logical system has got structure inside it. It has a potential for rewriting. Um, and it gets mapped onto something also with dynamics, but that system is not, a mathematical system. That's not where it was initiated. But instead, it's the simply typed lambda calculus, which is a system of computation, which is powerful of arbitrary. It's a Turing. It's able to compute anything that a Turing machine that the Turing machines are able to compute. So again, just speaking loosely, we have natural deduction on one hand. I never know what to write here, so I'll write cut elimination, but that's kind of leaning into some of the problems of the history of this work. I'll also write detour elimination.
I think a natural deduction buff would probably be screaming to think of cut elimination in natural deduction. Why not just say detour elimination?
Because absolutely nobody in the community thinks about detour elimination as beta reduction or as the computational component. I mean, it so obviously is, but everybody talks about all of the theorems out there are the cut elimination theorems. And I think that we're now at a point where people loosely refer to even detour elimination as cut elimination, which I think is really, really silly. I think that's a mistake. I'm the type of person where I would say detour elimination, right? Because that's what it is. But if you go and read the like Curry's paper and Howard's paper, they're talking about cut there because their system has got cut inside it. And so that begs the question, whatever. So it's a bit of a painful product of history, this little point here. I write both in case anybody wants to Google this. So if I wrote detour elimination and you Google it and you see cut elimination everywhere, that's why. Okay. And then the other one is the untyped, no, sorry, the simply typed. The simply typed lambda calculus. And the heading here is logical, and the heading here is computational. So if you're not familiar with these systems, to give them a one-sentence overview, the natural deduction was invented through thoughts of philosophy and of logic. We were trying to ask ourselves, what is meaning? What is proof? What does it mean for a statement to be true? What does it mean for a proof to be correct, etc.? And then the inventor, Gensen, decided to be as formal and rigorous about it as possible, try to create a mathematical object out of it. And in fact, he came up with two different systems. But the important thing is this dynamics that exists in the system. So there's a particular rule, which is the modus ponens rule. If I know P and I know P implies Q, so that's an implication, then we can deduce Q. And this rule is admissible. What we mean by admissible is that any statement that can be proven using it, there exists another proof of the same statement that does not use it. So this rule is not crucial when it comes to expressivity and provability. Moreover, it's not just that there exists a proof that does not use it, there in fact exists a process for eliminating the instances of modus ponens from a proof that uses it. And that rewriting of the slow elimination, so you lower the complexity. So you give me a proof that uses modus ponens, we define a notion of complexity of that instance of modus ponens, and then I can transform the proof into a new one that has a strictly lower complexity for that particular modus ponens rule. And so you just keep doing that until eventually you've eliminated all of them. So that algorithmic process is the dynamical content of natural deduction. And on the other hand, we have the simply typed lambda calculus, which is a system of computation. So the dynamics of this system comes from beta reduction. And there are quite a few subtleties involved in defining beta reduction, to the point where I don't want to give an over the head view of it. You could write down the beta reduction rule, but I think that would be misleading. But the point is that we're looking at computation via substitution. So if I have formal variables and I have words or strings that are built out of those formal variables in a prescribed way, then maybe just by performing substitutions of words into variables and then simplifications, I'm able to produce a system of computation, something that I can literally perform addition, multiplication, and the rest of it. And indeed, such a system exists. It's a simply typed lambda calculus. And the current Howard correspondence proved, again, I have to say, quote unquote, proved an isomorphism between these two worlds. But when it was originally written, it wasn't described in terms of it wasn't described using the language of category theory. So what do we mean by isomorphism? What do we mean by equivalence? And also you had to only take the closed terms on the lambda calculus side. So it's a semi-dissatisfying isomorphism. And that's what I'm going to write down.
If you don't mind me echoing a sentiment I'm sure you agree with, people should interrupt, or rather not interrupt. They should contribute by asking questions at any point. And Will is very much eager to hear your questions, either out loud or in the chat.
Yeah, of course. Thanks. In fact, I think I'm saying some pretty provocative things. So please call me out on that. But I believe all of this to be absolutely true. And the some work, just to briefly nod to it, I won't write anything down at all. But just to bring this back to category theory, is Dan and myself looked at this and thought, well, okay, we've got two different contexts, and there's some kind of relationship between the two of them that has been etched here. Why not just construct a logical category on one hand and a computational category on the other, and see what we need to do in order to construct an equivalence of categories. And indeed, we did that successfully. So we called that the Gensen-Mintz-Zucker duality. And I think that I have links to that somewhere, either it's on my webpage, obviously, and Dan's, but it's on the Shadows of Computation one. It's buried inside one of the exercise sheets. It might be week 3, which is not up yet, but you'll get a link to that at some point if you're interested, or you can just message Dan or myself about it. But I'm not putting that here in order to boast. I'm putting that here to say the actual content of our work was the Curry-Howard correspondence, which already existed, and indeed it did reflect an equivalence of categories, but the original way that it was presented was not done in that way. However, I would definitely say that it's good to think about it like that. And this is a concrete example of the syntax and semantics drawing that I had on the first board. On the left-hand side, I have this logical syntactic category, and the elements are equivalence classes of statements in exactly the way that I said. And then on the right-hand side, we have a quote-unquote semantic category. So we've got actually, that's kind of a complicated part of computation. What is that? Is that syntactic or is that computational? I think that's a very difficult philosophical question. But let's just go ahead and say we have some kind of system with some kind of dynamics in place that can perform what we would think of as real math. Like it can perform addition, it can perform multiplication, etc. And then there does exist an equivalence of categories between these two things. So that's an example of where the language of category theory is very helpful. Okay. So that's a computer science motivation followed by a logical motivation. But what about a mathematical motivation? Indeed, it was in mathematics where category theory was discovered. So maybe this is where the meat and the potatoes are. the the question that I want to ask, I want to ask a meta question. So before giving you the motivation, I want to ask, what does it mean to motivate mathematics, right? So maybe this question is a bit easier to answer in the other two realms. With computer science, we have computing systems and we want to understand them. With logic, we have philosophical questions that we want to apply rigor argument to. With mathematics, what does it really mean to motivate a theoretical mathematical idea? This is the reason why I'm asking this is because of the course's other goal, which is to give some kind of get you thinking about how you would present mathematics or any theoretical idea. So this is important. Let me in fact write it down. Okay. And this is the kind of thing that you could wax lyrical about all day long. And indeed, people do. I'm a strong contributor to that noise in this world. But something that I can say that would be helpful is you need to show that there exists an idea inside the work. And this is very subjective. This is kind of like the artistry of mathematics. You know, you go and watch an opera and you think that it was completely hollow, whilst the person next to you was moved to tears the entire way. But my opinion is that that's a very good thing. What a crucial part of being a mathematician is the connection to the emotional side of performing mathematics. So you need to ask yourself, am I compelled by this idea? Am I looking at this and having the sensation of this is undeniable? There is something here. And when I perform this calculation, or when I write down this definition, or when I draw this relationship, whatever it might be, have I stumbled across an idea, and over the years and years and years of training and developing the mind of a mathematician, what constitutes a genuine idea and what doesn't is one of the most important parts of being a mathematician. So I would really encourage everybody to be thinking about this inside yourself because you can start doing it immediately, right? And you're allowed to have opinions even if you feel like you're not experienced or you haven't done much math or you're not a mathematician and things like that. I don't care whether you're formally a mathematician or whether you've done it for years or only a few minutes. I want to know whether you are compelled by a particular idea or not. And can you find that inside the mathematics that you're doing? Right. So let's start off by seeing if I can show to you that there is an idea that exists that is very subtle. And then I'm going to proceed to try to make that idea apparent. And that's where that's where the title of the lecture comes. So what do mathematicians do? They make the subtle apparent. And that's what you need to do when you're motivating mathematics. Okay. And the example that I had here um, was was a relationship between a finite dimensional complex vector space and its dual. So we're going to talk about so recall recall that if V is such a space, then we denote by V star the dual, and the underlying set is a set of linear functionals from V to C, and all that is a function which we require to be linear. And then the vector space structure, so the scalar multiplication and the addition, is just performed component-wise. So z times psi will just perform the function psi and then multiply by z afterwards. Okay, and I want to sketch two relationships for you. One of them is an isomorphism between such a vector space and its dual, and the other one is going to be an isomorphism between such a vector space and its double dual. So I'm going to define these two isomorphisms for you, and then we're going to look at them, and then I'm going to try to make a point. So first, let's choose a basis for the vector space V. Let V1 dot 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 Vn be a basis for V. Then I'm going to define a linear functional. So I define Vi star for all I equals 1 up to n to map from V to C. Oh, wait, I guess I'm defining this kind of dodgily. Yeah, sorry, I need to backpedal. So let Vi star be defined by linearity and the rule Vi asterisk Vj is equal to 1 if I is equal to j, and 0 if just otherwise. Okay, that's a bit better. Then I can also define for an arbitrary vector, v inside v, v asterisk to be linear. And so that I guess, no, sorry. I'm making a meal out of this. Okay, let me go back and make the first point, and then I'll come back and define where I'm actually going to use v star. So what I want to say is there's a simple claim, which is that v1 star dot 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 vn star is a basis for v dual. Okay, and then I can define a map. I can define phi to go from v to v star. And what it does is it takes a vector v, and we observe that we can write it as a linear combination of elements in the basis. And then we map this object to this linear functional, right? So it's clearly linear by the way that I've written it. And the action is just to turn the basis vectors vi into their corresponding dual elements, which I've defined up here. Okay, and this is an isomorphism. It's obviously an isomorphism. You can see a very obvious reverse map. The difficult part is proving that this is indeed a basis for V star. But once you've got that, the proof of this claim follows easily. And working out that this is a basis for V star is one of the exercises for this week. Okay, so now I want to define a different isomorphism, one from V to V double dual, and then I want to compare it to this. I've picked the worst possible break in the boards to do this, but that's okay. So we're moving over here. Am I moving over to the ones with all the drawings on it?
Yep. Just clear them so they get saved anyway.
Okay. Okay, so now what I want to do is define psi to go from V to V double dual. And what it does is it takes a vector V to a linear functional, which takes an element of the dual and then gives you a complex number. And the way that this works is if you give me an element of the dual, I simply evaluate it at V. Okay, so this one's kind of easier to write down. And in fact, that's kind of the point. I think I just saw things in the chat. Oh, no, not important. Okay. And this is also an isomorphism.
Since I was briefly confused, the V star inside the bracket there is actually the domain of the function that's being defined in the next line. I thought at first it was meant to be an element of V double star or something.
Oh, I see. Yeah. Yeah, the notation. So
maybe you could just write down the formula for psi. Psi of V of phi is phi V or something, just in case this convention where you write a function inside a bracket like this is not I think, universally understood.
Sure. So given phi v star. Okay. Okay, so there's just two different notations for the same thing. So you can think about it either way. And it's great that these are isomorphisms. We can go ahead and prove them. But that's beside the point that I want to currently make. I want to go back to what I was talking about with how you motivate mathematics. And I want to say there's an idea here. And the idea is that there is a distinction between these two isomorphisms. A distinction in concept. And the way that what I really want to put my finger on is I want to say the first one required a basis for V to be chosen in order to even describe down the map, right? Whereas the second one didn't. And the reason why this is important is because vector spaces aren't conscious of their bases, right? So what's a vector space? A vector space is a set along with two operations, and they need to satisfy this group of axioms, etc. But there's no basis that comes built into them. Sometimes there's a standard basis, but that's a coincidence of that vector space if that turns out to be the case. And even when there is a standard basis, is it standard from the perspective of mathematics, or is it just standard from the way that we like to interact with this particular object, right? So a basis is a thing that we use in order to get a handle on the vector space. So in order to understand it, we construct a basis and then use it to reason about it. So what that means is that the second map, psi, is a little bit more true to the structure, which is genuinely part of vector spaces. Whereas the first one kind of requires human intervention in some way. So let me write down the most loose and hard and fast thing we've ever seen written in a math talk. We're going to say phi is manhandled we need to introduce a basis to even define it, but psi is true to the structure of vector spaces. Okay? Now, watch a magic trick. So I'll move to the next board. In other words, the first map, so I'll say phi is not natural and psi is natural. And here, naturality is an actual word. So I'm no longer talking vaguely here. right? That's what the previous sentence was. The previous sentence was me as a fleshy, fallible human being trying to point to something that exists in the world and convince you that maybe we should go and explore it. The second sentence, this one, is a completely formal mathematical statement. And naturality is a concept that comes from category theory. Well, it was actually the other way around. So I believe MacLean was first exploring naturality, and then I guess on his first sentence is manhandled. So the first sentence is manhandled in yeah, exactly. Whereas the second one is an actual sentence. Okay, so this concept of naturality was observed in various aspects of mathematics and then abstracted to the concept to the realm of category theory. But this was the birthplace, right? And you can see that we saw a phenomena and then explored it and came up with formal theory and language that then was able to make this completely subtle and blurry point night and day, right? Like there's nothing similar between these two maps. One of them is natural and the other one isn't, right? So you can see that we've succeeded in our goal of making the subtle apparent, and we discovered mathematics by finding an idea using our artistic relationship with mathematics in order to believe that there was a there. And then we explored it, developed theory, and what came out of that was category theory, which allowed us to non-vaguely distinguish these two concepts.
Well, I disagree with that. You could clearly say right now what it means without introducing a single term of category theory, right?
Yeah, I guess that's true. So let's say
The proper context for fully exploiting the notion and understanding its generality is category theory, but yeah.
yeah. Well, yeah. I mean, you're right. You normally describe naturality in terms of functors and yeah, but you can clearly write down what it means for a map to be natural. So are we happy with this sentence? We'll define naturality later, but it has a formal definition and it led to category theory. Okay, so that's just a historical comment now, and that's fine. Okay, so that's motivation. Next step is to define category theory. Does anybody have any questions or comments or hopes or desires? Will, I really wanted the course to be like this or like that. Does anybody have anything that they feel like mentioning at this point? Okay, if not, let's define a category. I'll move over to the next two boards, please.
Do you think you're gonna have enough board space
In
for storage?
total, or
Yeah.
yeah, I think I'll be fine.
I'm just wondering if you should maybe continue using the bottom half of that board, or are you gonna move on to the next board?
So, in my experience, a category requires exactly two boards to define. So it kind of makes me want to jump over here, but no, I think I'll be fine.
All right, cool.
I'll I'll optimize later if needed. I'm also feeling confident. Okay. Definition. Category consists of the following. A collection of objects for every pair xy of objects a set hom xy of morphisms and morphisms are normally denoted f x to y, and morphisms come equipped with domains and codomains. So that's with domain x and codomain y. Wait, let me think for a second. So, yep, for every triple.
We got a killer question already.
Do we?
What is an object?
What is an object? Yeah, no. Let me finish the definition, and I'll come back to that. One thing I can say to help you read this, though, is that everything that's underlined is a definition, right? And so one shortcut answer is, well, that's what I'm defining. So a category consists of a collection of objects, and what's an object? Well, man, it is a killer one.
It's just a convenient word to use in the meta-mathematics for an element of this set with this structure, as though a group element you might refer to as a symmetry or something, but the word has no content.
Yeah. And the word having no content is what I was trying to say with the underline, right? It's a definition. I haven't performed math, and I don't have an a priori definition. I'm saying that these are the objects, or category consists of them at least. For every triple of objects, x, y, z, a function that's fine. And the last piece of data is for every object x, an identity morphism. Which is an element of hom x x. Okay, that's not the end of my definition, but it's the end of the data of my definition. So on the second board, we say subject to. So here are the constraints of a category. It's basically just associativity of composition and the fact that identities act like identities. So okay, and I'm suppressing the subscripts here, but you should be able to infer them from context. So when I introduced the function composition, which is the little circle, it had the subscripts, but we don't need to carry that around all the time. It's suppressing. Okay, and that condition is often referred to as associativity of composition. So maybe I'll write that. And then we need identities to act like identities. Cool. And that's the end of my definition. Yeah. So subject to or such that, whatever you want to say. But yeah, all I'm doing here is I've described the data on the first board. That's what a category consists of. And then the conditions that they're required to satisfy is the second. Okay. Now, a few words are in order. This is a very abstract definition, okay? And a lot of the categories that you will encounter will have morphisms and objects which kind of reflect the notation of the category. So let's look at how I wrote down morphisms. A morphism f from x to y, right? Is just notation for a morphism f with domain x and codomain y, but these words are all completely meaningless. Like, what is a morphism with domain x and codomain y? Well, it's just an element of this set hom xy, right? And that set can consist of anything, just as long as it satisfies the criterion on the right. So the canonical example of a category is the category where you take as your objects all of the sets, and you take your morphisms. So the Hom set x comma y is the set of functions f with set theoretic domain x and set theoretic codomain y. And so there you see that all of the notation kind of lines up, and it's maybe a bit simple to think about. But there are also categories that don't look like that in the slightest. So if we think about the syntactic categories that we were talking about earlier, you might have two different statements, and then a morphism from the first statement to the second is a proof that the first statement implies the second one, right? So there, a morphism is a proof. It's not even a function or a map. Well, I mean, I guess it could be thought of in that way, but instinctively, we don't think about it like that. Okay, let me address some of these questions. Maybe I missed a question or something. Okay. Okay, so examples. So there's the category set, whose objects are all the sets, and a morphism f from x to y is a function f with domain x and codomain y. Okay, so the conditions of a category are very clearly satisfied. Associativity of composition is very easy to prove, and identity functions are literally defined in this way. They just map an element to itself. inside the set. So if I pre-compose or post-compose with an identity morphism, I just get the same morphism, right? So that's a super simple, intuitive example of a category, but I really don't want you to start thinking that all categories are sets and function like, right? Because there are other categories that are like that, the category of groups, the category of rings, the category of topological spaces, etc. But they're not all like that. And so we need to appreciate how abstract this definition really is. So let me define an example like that over on the other boards. Oh man, that drawing made me laugh.
That's great.
It's so good, right? It's so creepy. Okay, so let's recall that a poset or a partially ordered set.
Oh well, you'll have to move a little bit to the left. The org cam's getting the wrong boards. Yeah, it's all good. Yeah.
Okay. Consists of a set P and a relation less than or equal to on P satisfying reflexivity for x and P, x is less than or equal to P, and what is it? Transitivity and anti-symmetry. So transitivity for x, y, z, an element of P, if x is less than or equal to y, and y is less than or equal to z, then x is less than or equal to z. And anti-symmetry for x, y, an element of P, if x is less than or equal to y, and I guess I'll put a word anti as well, and y is less than or equal to x, then x is equal to y. Okay, and we can view any poset like a category. So we can say define the category, like fancy P, I guess, whose objects consist of the elements of P and where there exists a unique morphism f from x to y if x is less than or equal to y. Okay, so can you see that this category does not have morphisms, maps, or functions in any way, right? It's a marker. So a morphism f from x to y is a symbol which informs you that of the fact that x is less than or equal to y, right? So if you were to look at the Hom set from x to y, where x is not less than or equal to y, then that set is just the empty set, right? And if you were to look at the Hom set from x to y when x is less than or equal to y, then that Hom set consists of a unique element. And it doesn't even matter what you call it, f, bullet, asterisk, who knows, who cares, right? But it's just a marker. It just informs you. So if that set is occupied, then X is less than or equal to Y. And you can go through and you can prove that this is indeed a category, and um, all of the axioms kind of line up, I suppose, except for anti-symmetry. You don't really need it. But transitivity is telling you that I have compositions, right? So if I have a morphism from X to Y, and I have a morphism from Y to Z, then there exists a morphism from X to Z. And reflexivity is giving you the identity morphisms. So there always exists a morphism from X to itself. The fact that composition with this just acts identically comes from the fact that there exists a unique morphism every time X is less than or equal to Y. So if X is less than or equal to Y and Y is less than or equal to self, then there only exists a unique morphism from X to Y, which is the same statement that X is less than or equal to Y, right? So you can think about it from the perspective of posets as it's redundant to inform me that Y is less than or equal to Y because they all satisfy that property. So telling me that X is less than or equal to Y and Y is less than or equal to Y is equivalent to the data, or it's equivalent to the fact that X is less than or equal to Y. Okay, and I had some exercises surrounding that as well in the shades. Let me check the chat again. Okay.
It's also interesting that like posets kind of, or the poset perspective kind of tells you that categories are, you could think of them as a generalization of posets, where like all of a sudden the uh, rather than just a binary relationship between objects, there's like a hum set of possible, you can have multiple sort of relationships rather than like either empty or not empty hum set.
Yeah, and I've heard people talk about posets being a better example of an arbitrary category than the category of
Mm.
sets being an example of an arbitrary category.
Because you can take any category and sort of crush it down to what's called the skeletal category, I believe, where
Mhm.
you, if you have, if your hum set is non-empty, you compile it down to a single unique element, and if it is empty, then you leave it, and then you end up with a poset.
Mhm. Okay, good. Excuse me. Okay, so that's about it. I guess I finished. I guess I finished quite early. Um, are there any questions? And if not, and if people are interested, I could talk very briefly about some of the set theoretic foundations of categories, because you might have noticed earlier that I spoke about the objects in a category being a collection of objects, but then for every pair there was a set. So there are subtleties that come up there. And also, I've written on the board that an example of a category is the category of sets, where the collection of objects are all of the sets. But those familiar with Russell's paradox will tell me that that such thing doesn't exist. So there, there, there are solutions to these possible foundational queries, but they're really difficult and they require a lot of prerequisite knowledge in first order logic, etc. So it can be a massive distraction, but I'd be happy to talk about that if anybody was interested. But let's start off with questions. Are there any questions from what I actually covered today?
Well, first, thanks, Will.
You're welcome. Okay, so what I'm going to do is make a transition. I'm getting the time right? I've got another 25 minutes. Is that right?
Yeah, yeah.
Yeah.
Yeah, I thought so. Okay, cool. So let's call that the end of the lecture, and that's the content for today. And let's transition out of lecture style so we can go into seminar style, more conversational, and talk about some of the foundational uh, problems and solutions that come up when dealing with categories in the using set theoretic foundations. Okay, maybe I need my notes for this. Let me load it up. Yeah. Okay. Okay. So the point is, um, if we said the objects of C is to be a set.
If you don't mind me derailing you, Will,
Yeah.
maybe let me hit you with a few other questions, imagining myself to be a curmudgeonly audience member who showed up even though they actually don't like categories. So,
Mhm.
category theory, I hear people talking about category theory all the time. Isn't it just some language? Why do I need it? Surely anything I can say with category theory, really the core of what's going on must be somewhere else. So
Mm.
why do I have to learn this strange abstract language?
That's a good question. Okay, so
Just
yeah,
tell me
this is
just tell me
one
the
of
good bits, man. Don't tell me all this junk with adjoints and functors and
yeah. Did somebody jump in and start saying something, or was that feedback? Okay,
no, I didn't
okay.
hear
So
anything.
this question gets asked all the time, right? So first, I'm an optimist, and I would like to see this as an opportunity. So I think that that's one of the fascinating philosophical questions of category theory. Is it just a language, right? And yeah, that's one of the common criticisms of category theory. You're forcing me into this whole new formalization and think about things differently when I can just write it all down in the terminology that I'm already familiar with. And that's better because if I were to do that, I can just do some goddamn math already. I don't need to waste my life designing a new language to then do the same math at the end of the day anyway. Well, what I would say there is what what is the line between language and mathematics? So I might give you a new way of describing things that you could write down in the terminology and the notation that already exists, but it's going to be so goddamn hard for you to do that. And maybe the opposite exists as well, right? Maybe there are some things that are really, really hard to describe using the language of category theory, but it's really easy using the other perspective. So that's natural. And what that tells you is that they're distinct perspectives. That's actually a good thing, right? Um, but what you want to prove is that there are indeed things that are easier to say using category theory than if you didn't use them. Where I personally first really gained an appreciation for the language of category theory, um, and this is what I always say to experts when I'm arguing with them about it, is there are some results inside algebraic geometry that are considered relatively elementary, but they're really, really, really nasty to prove. And some of the proofs require shifting the context that you're working in several times, sometimes really, really subtly. And what you're doing when you're changing the context is you're mapping between different categories, but you're telling me that you don't want to use that language, so I'm not going to. But the point is, there are some constructs that exist only with reference to the context that they're sitting inside. So, this is one of the points that I'll make later in the course. There are morphisms, for example, which are epimorphisms, whatever that means, when you view them inside a particular category, but they're no longer epimorphisms when you look at them inside a different category. So whether you want this thing to be an epimorphism or not, or whether you want to use that feature of it or not, depends not just on the object itself, but the context within which you're observing it, right? And what is convenient language for that context and those shifts in context that is not category theory? So universal properties are another really good example of this. Sometimes you need the construction of an object which requires consideration of the entire context to infer whether it exists or not. And what you might find is that the context you're currently working in does not allow for the existence of this object that you want. And and you might be tempted to change the object that you're after. Whereas with the language of category theory, you're prompted to change the context that you're sitting within. So you might shrink the category, or you might embed the category, find the object, work inside that different category, and then see if it reflects back into the original one. And the point is that this language gives you a perspective that allows you to create things and to use things that you wouldn't have found earlier. So is it really just a language? Like using the word adjoints to describe adjoint pairs is a really difficult thing to categorize from the perspective of philosophy. If I want to understand what that action is, have I merely described something with a choice of language that I've defined, or have I discovered a perspective which is provably distinct to other perspectives in that it can bear fruits, or did bear fruits, or does bear fruits that the other ones don't?
I'm
So
convinced.
what is
I've got the religion. So everything important about logic and computer science is to be found in category theory. Yes.
that?
Is that
I
right?
wouldn't go that far either. So one thing that we're wanting to do in the foundation seminar, which we've advertised a couple of times, is explore what happens when you really take category theory seriously. Because yeah, you basically find one or the other. You find these people that are like, oh, this is stupid, I don't want to learn it, so I won't. And you get people that are completely convinced of it and yeah, definitely religious toward it. So um, and I'm kind of in that boat. I was very swept away by category theory when I first got into it, and I loved its connections to logic and various other aspects of it.
Be
Um,
careful. There's literally a person called category theory standing behind you. So-
um, and so the question is, can you put your money where your mouth is, right? So don't don't wax lyrical with me endlessly until I believe that you've said such poetry about category theory that I must learn it. Don't do that. Instead, use it as a goddamn foundation, see how far you get, and I wonder if you get to a point where you say, damn, I really wish I had set theoretic foundations. It's really a shame that I'm using category theory to use everything. I have a concrete example of this. I was talking to my French supervisor about this. He made a really good point. So set theory has canonical subsets. So thinking really canonical representations of subsets, right? So if we talk really loosely, if I have the set containing A, B, and C, then I can take the subset containing A and B, right? But category theory would get confused because category theory would think about that subset as the equivalence class of isomorphisms, sorry, injective morphisms, uh, from the 2-point set into the 3-point set. So I could, yeah. So wait, how's the one?
well, any
Anything, sorry.
topos has that as well, right? Using the subobject classifier.
So, so how though, right? Because there we're using the
Well,
characteristic function
pullbacks
of
aren't
the
unique, but you could identify, if you just decide that subobjects really are maps into the subobject classifier rather than equivalence classes of things.
Hmm,
But yeah, it's a
hmm,
good point.
hmm.
But someone
Yeah,
asked,
yeah.
sorry, I was just
I
going
thought it
to,
was a really good point. So I would love to know whether that's truly a non-issue, right? And that's the kind of thing that I think you come across when you actually take it seriously. And so that's why we want to do that in foundations.
someone asked in the
But
chat, how does category theory map to Platonism?
yeah, it's a good question. So do you believe in Platonic existence of categories is what I would say first. Now, you're going to end up with a
Just for
highly,
context, we believe in the
yeah,
existence of dodecahedrons and algebraic varieties, and then the question is, do we also believe in the Platonic existence of categories, or are you just asking I think that's the question you're asking, right? Not like just a broad question of should we believe in the Platonic existence of any mathematical object, but do categories somehow deserve to be considered in the bucket along with, the Clyde 4 group or whatever? Or is that not what you mean? Well, I can't hear you. Maybe you're thinking very hard about my question. Maybe.
I can't hear me either.
Yeah, me either. Why don't we discuss both? So, should an object be considered platonically existential? That I think comes back to developing your mathematical artistry, and the argument and the debate of such things, I think, is an incredibly important part of doing mathematics itself. Um, I like to look at theorems. I like to see structure. I like to see relationships, and I like to see alternate paths that end at the same object. So can I arrive at this thing via many different directions, or is there only one like very uh, what's the word contrived passage of thought that I need to take in order to end up there? I also like consistency. I think that people all throughout history have believed that consistency is necessary for genuine existence. So, does that apply to category theory? Another major criticism of category theory is that it has no theorems. So, you might have heard this before. Does category have any theorems? There's the Oneida lemma and the Oneida embedding, which is very important and definitely a theorem, and we'll talk about that later. But kind of the problem is there's one. So there's that, and there are other theorems about category theory, but they pertain to category theory itself. So you have like the adjoint functor theorems, for example, but that's like in this category theoretic situation, you get this category theoretic, uh, you know, certainty of the remainder of that situation. So it's just like category theory proves stuff about category theory, but obviously it's going to do that. What we need is relationships between categories and other objects that we do have a Platonic belief in. And they are few and far between. I think that people are trying very hard to make this work with homotopy type theory, right? So you have infinity category theory, and it's hopefully deep connections with homotopy theory.
Well, we don't have to go that far. I mean, there's certainly a lot of theorems in algebraic geometry or algebraic topology or numerous areas, not to mention, I doubt it would be very easy to understand the proof of Fermat's last theorem without mentioning categories anywhere, as far as I understand that. So, to what extent are the theorems in category theory itself essential there? Well, you could say it's essential to adopting a point of view and way of thought which leads you to actually comprehend the argument. And to come back to a comment you made earlier, at what point is language, a sort of a pejorative word, that it's just language? And at what point is it language, the thing that separates us from the beasts? It's, I think it's a bit unfair to say that things like the adjoint functor theorem there's certainly arguments in topology itself, in homotopy theory, even way before infinity categories or homotopy type theory. There's constructions, the existence of certain spectra, certain sort of fancy topological spaces, things that play the role of topological spaces that represent certain operations you want to do. The known arguments for their existence is some kind of crazy transfinite induction that makes heavy use of category theoretic ideas. So, I think to To reject that would be a bit like rejecting the construction of the complex numbers because you don't believe in equivalence classes or something, right? I mean,
Mm.
are equivalence classes at the heart of that? Well, no, but you also can't even really conceptualize the complex numbers if you don't admit that language and that way of thinking.
Mm. Mm. Yeah, I see.
Oh,
Mm.
there's another comment in the chat. To extend the
Yeah.
notion of context, as prisoners in the cave, we have access to shadows, but what gives us access to the true forms of those shadows? Riley, you're up. Yeah, what say you, Billy?
Wait, why me?
I don't know, because you're quiet and you've just had your teeth out, so I want to make you speak.
Well, I had like a I guess a related comment slash question, which is, uh, Will, you are alluding to like choosing category theory over set theory, or the other way around as like a foundation.
Mhm.
But the sort of comparison, it doesn't feel like they're sort of like it's sort of apples and oranges in the way that like the description of the definition of a category is very like schematic thing where it says this is like, uh, bring your thing to the table, and this is a means of asserting that it's a category. Whereas with like set theory, it's sort of a, like it's still kind of abstract, but it's sort of more like, uh, concrete in that it's not like, bring something to the table and I'll tell you whether or not it counts as an empty set or something. It's very it's more like this is the thing that the empty set is, and like it
Mhm.
like all the sets are just what they are, and that makes them very like, uh they're like your building blocks that you use, and there's no like they are things in themselves. It is the sort of way that story is told, but it's not really like that for category theory. And so the way, like there's a sort of standard way of explaining category theory as like this, like sort of bootstrapping the category definition with like the ZF set theory context, um, where like you say very specific things about your sets or collections or classes or whatever. Um, I don't like, but I don't really know how you do it the other way around, or just like using category theory without like the sort of set theory view on it. Um, like maybe there's a different flavor of like talking about and describing categories with like type theory or something, but like I don't know. Could you argue for and against like the premise of even thinking of category theory as a thing that could be a foundation for something? Because like I
Hmm.
think based on my summary there, it sort of doesn't really meet the requirements of like a starting foundation in a way that set theory would.
But couldn't you just like remove some of these helpful categories from your mind and it makes it a bit easier to imagine? So, like the category consisting of three objects, identity morphisms, and one morphism from a random one of those objects to another. Like that category. So, those 3 points and 4 lines, that graph, right, is an example of a category. And then all the other completely archaic, like, you know, all of
Yeah,
those.
so you're giving like a specific example of a category, and because it's sort of simple and small enough, you like you're using points and lines as a sort of example of what the objects and morphisms could be, but like that doesn't speak to like what they can be in general, and like points and lines might not really make sense for all categories. So it still
But
sounds like you need to still bring something to the table to like make sense of what the things you're talking about with the language of category theory are.
so in what way does set theory not do that though? I mean, we think about sets in the same way. It's like a group of stuff. We have this idea of the set of the integers, right?
Well, we're talking.
But
I mean, you can formulate a foundations with. I mean, just take a first order language which has the axioms of a category in it, and then you can form statements using that in much the same way as you could do using the type formation operations that you would have if you took the first order theory of ZFC. That's a perfectly valid starting point. You could say that maybe you can't say very much using that, and that's why you wouldn't just have the axioms of a general category there. If it was attempting to be foundations, you would put in something like the axioms of an elementary topos at the very least. But I don't think the epistemological status of the terms that are happening there varies too much from the status of terms that would appear in the first order theory of sets.
okay.
And regarding the canonical, yeah, I would disagree a bit with that. I think that set theory is, well, we have conventions about what integers are, right? And even people are somewhat surprised sometimes when I disagree with them about what the integers are because they prefer some other ordinals to the von Neumann ordinals, right?
Mm.
So, maybe somebody thinks that 1, 2, 3 should be the empty set wrapped some number of times in curly brackets, and that's what they think n is, and then I say, yeah, you could do that, but then the elements of n won't be cardinals because they're not ordinals. You really have to do it blah 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 blah, blah, right? Well, that's kind of weird for something that's supposed to be kind of canonical, and it is what it is, right? It is what it is, except everybody maybe has a slightly different private convention for what it is, and it doesn't matter because why? Well, we're all using something that has the same universal property, namely, the axiom of induction and the successor operation, and that's all we need to communicate.
Yeah, that makes sense.
So I'm not sure that. I mean, I do think you're right to some degree. So there's a sense in which, as Will's comment was making earlier, you kind of maybe think of set theory. Like there's something about the terms that appear in set theory being, more rigid than the things that you would find in a category theoretic foundation. I guess that's true.
You were saying before that, like, you formulate category theory axioms with first order logic, and then they're on the same sort of playing field. But to what degree do you also need to like some of the sort of definition of a category wherever it mentions sets, and when you introduce Hom sets, like there's sort of set theory like rules that we make use of when doing in category theory that sort of relies on those Hom sets, which are sets and all the properties of sets, right? So like, is the sort of statement that you could use either set theory or category theory as your foundation, is it like am I actually just still seeing you write all those set theory axioms within the category theory foundation anyway?
Yeah, to be honest, I don't know, and somebody who's thought about this could easily think this is misleading what I'm about to say, but I imagine, well, okay, a naive approach to set theory just identifies sets with the predicates that define them, right? So rather than say that F belongs to the Hom set of morphisms from X to Y, why not just have a 3-place predicate in your language that says that P bracket F comma X comma Y is true? That means F is a morphism from X to Y. And then you can just make sentences with P, right?
Yeah, the trouble is, okay, well, I just have to think. So I'm very familiar with like first order logic with one sort, and what you described is definitely not a one sort of thing.
Yeah. So what? Who said I should only have one sort?
Pardon?
Well, that seems like a. Oh, I don't see any need to only have one sort in my language.
Yeah. Okay. I was just sort of. My comment was just that I'm used to like thinking about only one sort, and so I'm trying to access the subtleties here, and I'm just identifying that there's that the predicate you were describing has like there's this object sort and the and a morphism sort.
We could easily go off into the weeds on this. Maybe it's a good time to wrap up. Are there any other questions for Will? I mean, this can continue, obviously, but maybe it's good to mark the 1.5 hour point as a time to hop off the train if you are feeling trapped. Any other questions for Will or contributions to the discussion?
Before people leave, we should also reiterate that Wednesday night at 8 p.m., so like an hour before it is now, but on Wednesday, will be the scheduled weekly exercise session. And the direction that I'm pointing back there's 3 more sets of boards that that you're welcome to use for the exercise sessions. And you're also very welcome to find your own times to meet up. And yeah, that's all I have to say about that.
The exercises are on the webpage now, right?
Yeah, there'll also be like a weekly SOC channel with all the relevant material in the first message.
Awesome. Okay, thanks everyone for coming. Thanks, Will, for speaking. Thanks, Billy, for building all this and making it even cooler than it was before for this. And especially thanks for everyone for showing up for the first lecture of our second class. I don't know if you have to go, Will, or if people can hang around and ask you further questions.
I do need to go, but I can stay for another couple of minutes in case anyone does want to ask something.
Great. Okay. Well, I'm going to stop the recording anyway, and I'll catch you all later.
Okay.